Chapter 1, Module 1. In this course of set theory, we shall mainly discuss various fundamental principles. We begin our tour with several facts of finite sets and countably infinite sets. In this module, we shall establish certain important but obvious results concerning finite sets, and in doing so, we shall see how the logic is built, and that helps us understand whether these results can be stated for infinite sets too. So, we begin with finite sets. In what follows, we use the following symbols. To denote the set of natural numbers, we use n. For set of integers, we use z, and r will denote the set of real numbers. A set A is said to be finite if either it is an empty set or there is a bijective map from A to the finite set 1 to n for some positive integer n. Such n is known as the cardinality of the given set A. If A is empty, then A is said to have cardinality 0. Now, the following is a very obvious but useful result. Suppose n is any positive integer and A is a set, we take a point A0 from A. The theorem states that there exists a bijective map F from A to the set 1 to n plus 1 if and only if there is a bijective map G from A minus A0 to the set 1 to n. Now, of course, this theorem is very natural and quite intuitive, but we shall establish this result to understand how the logic is built. Suppose there exists a bijective map F from A to the set 1 to n plus 1, and we assume that the point A0, a specific point of capital A, is mapped to the point n plus 1. So, this is the first case when we are assuming that A0 is mapped to n plus 1. So, we define a function g from A minus A0 to the set 1 to n defined by gx equal to fx for all x taken from A minus A0. And of course, this is a bijection, and now we suppose that A0 is mapped to some point m which is lying in between 1 and n. In this case, since F was a bijective map, there must be a pre-image of n plus 1 inside capital A. So, assume that the pre-image of n plus 1 is A1. That means, F of A1 is equal to n plus 1. Now, of course, F being bijective, A0 cannot be equal to A1. Now, define a function h from capital A to the set 1 to n plus 1 by h is equal to fx for x belonging to A minus A0 A1, h of A0 equal to f of A1, and h of A1 is equal to f of A0. Then h is definitely a bijection. it is simply changing the role of A0 and A1. So, the required bijection G from A minus A0 to 1 to n is defined by Gx equal to Hx for every x belonging to A minus A0. Conversely, suppose G from A minus A0 to the set 1 to n is a bijection. We need to define a function f from A to 1 to n plus 1. We define it by mapping all the points x from A minus A0 to the point where G is mapping the point. That means, for every x we choose from A minus A0, fx is equal to Gx. And if we pick the point A0 from capital A, then we map that point A0 via the map f to the point n plus 1 in the set 1 to n plus 1. And of course, this is a bijection and it serves our purpose. Next is another useful but very natural to understand result. Suppose f is a function from A to 1 to n, which is a bijection for some n belonging to capital N, and capital A is any set. If B is a proper subset of A, then there does not exist any bijection G from B to the set 1 to n, but there exists a bijection G from B to the set 1 to m, where m is some integer less than n, provided we choose B as non-empty. Suppose we start with a proper subset B of A, which is an empty set, then there cannot exist any bijection G from B to the set 1 to n for any n chosen from the natural numbers, because whatever the value of n, the set 1 to n is non-empty. On the other hand, we have chosen B to be empty, so there cannot exist any bijection from B to that particular set. Now we apply mathematical induction on n to prove this result. Let us suppose n is equal to 1. Then capital A has a point, say small a, and therefore its only proper subset is B equal to empty. So the result holds as we have shown earlier. Now assume that the result holds for some n. We shall establish the result for n plus 1. Let f from A to the set 1 to n plus 1 be a bijection and B a proper subset of A. If B is empty, the result holds as we have shown earlier. So we assume that B is not equal to empty set. Choose any point A0 from B. Since B is properly included in A, we always have a point A1 from A minus B. So there exists a bijection G from A minus A0 to the set 1 to n, as we have seen earlier. Now again, B minus A0 is a proper subset of A minus A0. By induction hypothesis, there does not exist any bijection H from B minus A0 to the set 1 to n. So, either this set B minus A0 is empty, or else there exists a bijection K from B minus A0 to the set 1 to P, where P is an integer strictly less than n. Using the previous result, there does not exist a bijection H star from B to the set 1 to n plus 1. Now, if B minus A0 is empty, then there exists a bijection K star from B to the set 1, because B minus A0 is empty means B is the set consisting of a single point A0. For if B minus A0 is non-empty, then as a bijection K from B minus A0 to the set 1 to P exists, we get a bijection K star from B to the set 1 to P plus 1. So, in either case, there exists M which is less than n plus 1 such that a bijection K star from the set B to the set 1 to M exists as desired. Following very natural but useful corollary of the results. If A is finite, then there is no bijection from A onto a proper subset of A. Let us try to prove it. If possible, let there be a bijection F from A to B, where B is a proper subset of A. Since A is a finite set, there exists a bijection G from A to 1 to n for some n belonging to the naturals. Now, we consider the composite map G composed F inverse, which is a map from B to the set 1 to n. Since composition of bijective maps is still a bijective map, G composed F inverse is a bijection, but that contradicts the previous theorem. Now, we state another corollary, that the set of natural numbers is not finite, and secondly, the cardinality of a finite set is uniquely determined by that set. Why the set of natural numbers is not finite? Because we can get a bijection from n onto a proper subset of n as described here. Let us consider a map F from n to n minus 1 defined by Fn equal to n plus 1 for every n belonging to n. Then it is a very easy exercise to check that F is a bijection. In view of the last corollary, n cannot be finite. To prove the second one, let us take any m which is strictly less than n, and suppose F and G are two bijections from the set A to the set 1 to m and to the set 1 to n respectively. Let us consider the composite G composed F inverse. Since F is bijective, F inverse exists, and it is a map from the set 1 to m to A. So, the composite G composed F inverse is a map from the set 1 to m to the set 1 to n, and of course, it is a bijection. Since the set 1 to m is properly contained in 1 to n, we have chosen m to be strictly less than n, and therefore, the initial segment 1 to m of natural numbers is strictly contained in the initial segment 1 to n of natural numbers, and this is a contradiction. In the next corollary, we establish that any subset of a finite set is always finite, and if B is a proper subset of a finite set, then the cardinality of B is strictly smaller than the cardinality of A. Now, if B is a non-empty set, we have the following equivalent conditions: that B is finite is equivalent to there is a surjective function from a section of positive integers onto B, and that is equivalent to the third one, that is there is an injective function from B into a section of positive integers. This is a very useful result, and we shall see that this result can be established in case we take countably infinite sets. Now, let us try to prove this result. We wish to show that 1 implies 2. Since B is non-empty, there is some bijection F from B to the set 1 to n for some n belonging to the natural numbers. Hence, its inverse serves the requirement. Now, if we take 2 as our hypothesis and try to prove 3, then if f is a function from 1 to n to the set B, and we know that f is surjective, then we define the map G from B to the set 1 to n by GB equal to smallest element of f inverse B, where f inverse B stands for the collection of all members which are mapped to the point B. So, it may not be a singleton. Since it is a surjective map, it may be a set containing more than one element. G is uniquely defined by the well ordering property of the natural numbers, and using the fact that f is surjective. What do we mean by that? If we take any point B from capital B, we have to have one element as its image in the set 1 to n. Now, since function f is surjective, each f inverse B is a non-empty set, and since it is a non-empty finite set, we can pick the smallest element from that, thereby define GB uniquely. To show that G is injective, so for any two points B1 and B2 from B, with B1 not equal to B2, we have F inverse B1 intersection F inverse B2 is empty. So, the smallest element of F inverse B1 and that of F inverse B2 are distinct. Hence, GB1 is not equal to GB2, which shows that G is injective. Finally, for 3 to 1, we start with a function f from B to the set 1 to n, which is injective. Consider the image of the function f, which is inside 1 to n. Then image of f is a finite set, and hence there is a bijection G from image of f to the set 1 to m. Clearly then, G-composed f is a function from B to the set 1 to m, and it is a bijection, and that proves the set B is finite. Finally, as a consequence of this result, we have that finite union of finite sets is finite, and finite Cartesian product of finite sets is also finite. Now, to establish that finite union of finite sets is finite, it is enough to prove the result for two sets. If we take A and B are any two sets, then there are three possibilities. Either both of them are empty, case 2 is either of the sets is empty, and the final case is none of them are empty. So, if we take A and B both are empty, then clearly A union B is empty and the result holds. For if either A is empty and B is non-empty, or B is empty but A is non-empty, then A union B is equal to B, or A union B is equal to A. So, in that case also the result holds. So, we choose A and B to be non-empty finite sets. Now, since they are finite sets, we have two functions f from the set 1 to m to the set A, and a function g from the set 1 to n to the set B for some m and n. Of course, they are bijections, and we define a bijection, rather we define a function k from the set 1 to m together with the set m plus 1 to m plus n to the set A union B by k I is equal to f I if I is equal to 1 to m, and k I is equal to g I minus m if I is m plus 1 to m plus n. This map K is clearly bijective, and hence A union B is finite. Now, to prove the second part, that is, if A and B are two finite sets, then their Cartesian product is finite. We start with the case when either A or B is empty, then of course, the Cartesian product set A cross B is empty, and so the result holds. So, let A and B be two non-empty finite sets. For each A, consider the set singleton A cross B. clearly singleton A cross B is in bijective correspondence with the set B by the map pair AB is going to the point B. So, the set singleton A cross B is finite, and hence we write A cross B as union of singleton A cross B, where union is taken over all the members of capital A. Now, since capital A is a finite set, this is actually finite union of finite sets, and therefore, by the previous corollary A cross B is finite. So far, we have discussed several trivial facts about finite sets. The question is, can we generalize these results for infinite sets too? We shall see next that certain results can be generalized very easily to countably infinite sets. Before that, we define what we mean by infinite sets. As expected, a set A is said to be infinite if it is not finite. Moreover, A is countably infinite if there is a bijective map F from the set A to the natural numbers. A set A is countable if it is either finite or countably infinite. In case a set is neither finite nor countably infinite, then it is called uncountable. First example of countably infinite set is the set of integers. As we can easily see that a map F from Z to N given by f(x) equal to 2x when x is greater than 0 and minus 2x plus 1 when x is less than equal to 0 is a bijection. The product n cross n of natural numbers is countably infinite. Let us take the set A as the collection of all points x, y such that y is less than equal to x. We define a function f from n cross n to A by f(x(y) equal to x plus y minus 1 comma y. Then it is also a easy exercise to show that f is a bijection. Now, define g from A to n by gxy is equal to x into x minus 1 by 2 plus y, then g will be a bijection. Now, taking the composite g composed f from n cross n to n, we get the desired bijection, proving n cross n is countably infinite. The first theorem shows that if C is an infinite subset of n, then C must be a countably infinite set. To define a bijection H from n to C, we proceed by induction. Since C is a non-empty subset of n, C has a smallest element. So, define H1 is equal to smallest element of C. Let us assume that H1 to Hn minus 1 are already defined. Then define Hn is equal to smallest element of C minus H of 1 to n minus 1. The set C minus the image of the set 1 to n minus 1 under the map H is non-empty, and therefore, Hn is well defined. Now, H is bijective because first of all it is injective, can easily be seen, and it is surjective because if we take a point C from C, Hn cannot be finite and hence not contained in the collection 1 to C. So, there must be some n such that Hn is strictly greater than C. Suppose m is the smallest element such that Hm is greater than or equal to C. So, for all I less than m, Hi is strictly less than C, and therefore, C is not in the image of the set 1 to m minus 1 under the map H, that is the point C is inside C minus H of 1 to m minus 1. By definition of Hm must be less than or equal to C, and hence the choice for Hm is equal to C, proving that the function H is surjective and hence H is bijective. The following result generalizes a theorem for finite family. We have already seen this result for finite family. Here we generalize that in case of a countably infinite set. Suppose B is a non-empty set, B is countable if and only if there is a surjective map F from N to B, and that is if and only if there is an injective map G from B to N. To prove 1 to 2, we start with a countably infinite set B, then there is a bijection H from B to N, and consequently taking the inverse H inverse equal to F, we get our desired condition 2. Let B be a finite set. In that case, the definition of B says that there is a bijection G from B to 1 to N for some n belonging to N. Define a function f from N to B by Fi equal to Gi for I lying between 1 and N, and G1 if I is taken outside N. That means it is having the value starting from N plus 1. This F is a surjective map as desired. Now, to prove 2 to 3, we define G from B to N by Gb is equal to smallest element of F inverse B. Since F is surjective, each F inverse B is non-empty, and so by applying well ordering principle, we have G as a well defined map from B to N. G is injective because G B1 equal to G B2 implies F inverse B1 intersection F inverse B2 non-empty, which is not possible unless we have B1 is equal to B2. And the last one, that is 3 implies 1, is very clear from the statements themselves. Now, as a corollary to this particular result, we obtain that a subset of a countable set is countable. Suppose we take B as a subset of A. We know that A is countable, we have to show that B is countable. So, there exists an injective function f from A to N, and we consider the restriction of this map F to the set B. That means, F restricted to B is a function from B to N. This is also an injective map, and therefore, B is countable. The next corollary says that the product of N with itself is a countably infinite set. We have seen earlier that N cross N is not finite. Now, we prove that it is countably infinite. In view of the last theorem, it is enough to construct an injective map from n cross n to n. So, we define a function f as f n m is equal to 2 to the power n 3 to the power m. Suppose 2 to the power n 3 to the power m is equal to 2 to the power p 3 to the power q for some positive integers m, m, p, q, and we further assume that n is strictly less than p. Then we have 3 to the power m is equal to 2 to the power p minus n times 3 to the power m. But in such case, the left hand side is a multiple of 3, while the right hand side is an even number, which cannot be possible. Similarly, if we choose p to be less than n, then we get a contradiction. So, n must be equal to p, and therefore, the equation reduces to 3 to the power m equal to 3 to the power q, and thereby we get m is equal to q. Finally, one can establish a result that a countable union of countable sets is always countable. We have established in this module that finite product of finite sets is finite. Can we say that countable product of countable sets is also countable? We shall explore these kind of questions in our next module. With this, we end chapter 1, module 1.